It's this time of the day again for XinaBox Daily. I can see that the video feed is could be a little grainy because the internet, I think globally, but especially here is a little bit over capacity. So I'm doing a PowerPoint presentation only. Hopefully that's not too much strain on the video here. So it's a huge day for us. We have got our data from our ISS kit back. So the kit is still with our launch providers in California, but they have offloaded the data and sent us the data over email overnight. So today I'm going to talk about this little project here. So the important thing for us with this project was to make sure we could send xChips to the International Space Station and we could get some kind of data from it. So it's not like there wasn't necessarily the data we could get that was important. We just wanted to make sure that we could prove that we could actually send something to International Space Station. We could have our launch provider just plug it in. It was plug and play. It went up there. It generated data. It didn't fall over. It didn't suddenly crash in the middle of the whole thing. Considering there is absolutely no interaction with the kit. It's locked into a box. The whole box sent up there. The whole box is coming back. So I'm going to demonstrate how that looks like. But just understand that any data we could get here that could be useful was a huge plus for us. We just wanted to see if we could log a lot of data, our software didn't glitch, our xChip didn't glitch, and so on. So what did we send? Well, so we sent these 9 xChips. So we have a CPU here in the middle. MCU is actually the writing and microcontroller unit. And it's similar to the Arduino Zero. So it's a ATSAM-D21, which did all the collection of the data. We had a power unit. This is a PT01, so power generic number 1. And the thing with that is that it can take any kind of like power between 6 volt and up to 24 volts. And you can tie in the plus and minus on the DC volts on those 2 poles any way you want. So there's like, it protects for reverse power plugged in here. And then we have a RTC, which is named for real-time clock. What that does is that it keeps the time. So you can configure it up front, and then it'll know the time. Even if you switch it off, there's a battery on the back you will see just now. And even if it's not set, as soon as it's plugged the battery in, it will keep the time from then on. So we just have to have one time to refer to, and we can adjust all our timing, which is the case with our kit here. Then we have a particle sensor. Actually, we don't use it as a particle sensor. We use it as a heartbeat sensor, but it was originally meant for particle also. So we decided to put it in and just record some data and see maybe we could learn anything from the data. So we didn't have high hopes for this, but we wanted to kind of like see if there was kind of like any dust or anything like that we could pick up with that. Then we have a VOC, so volatile organic compounds, which is, can give us a CO2 estimate. And since inside that box there was like biological experiments running, we thought it could be interesting to see if they gave out any kind of like biological air, let's use that term. So VOC or and calculating a CO2 estimate. Again, we just try to have a number of different chips that we thought that could be interesting, not that we was particular nervous about if we got the right data, tested the right thing. Remember, it was kind of like more a study of being able to collect data than the individual data. Now, VOC here, we have this climate sensor SW12, and we also have the SW2, which both give temperature, humidity. With the SW2, we also get the VOC and ECO2. So we kind of like have 2 sensors to kind of like pick that up, so we could kind of like compare the data. And we also have like 2 weather sensor, climate sensor, whatever you want to call them, that gives us temperature and humidity, those kind of things. And we have the IMU. So IMU is the accelerometer, magnometer, and gyroscope in X, Y, and Z. So both the SI20 and the SI01 have that. So the SI20 here, the SW12 you see just above, and the real-time clock is not available on our store yet, but we use this thing here to kind of like see how it worked in space. The SI20 was originally also made for our satellite ThinSat program, and the SW12 is a weather sensor that is quite popular outside our SW01. The real-time clock is something that needed for a project like this thing here, and a lot of other projects where you can't use Wi-Fi to get the time there. You can't put a GPS in and get the time because this is inside a Faraday cage. So you have to have some other timekeeping, and that's where real-time clock comes in. On the back of this thing here, there's only, there's a lot of logos, but the important part is to see this SD card here, which actually collected the data. There's room for 32 gigabytes. So we went mad trying to log data. We kind of like didn't want to necessarily be in a situation where we couldn't log all the data. So we kind of like set aside data for 4 months, even though that we knew that the mission was completely less. So we had enough data capacity with a 32 gigabyte. We didn't use it all. We didn't even use a gigabyte. So there was a lot of space. And then this is the back of the real-time clock. So this is where the battery sits. So the circuit doesn't run on this battery. It's only to keep the clock passing of the RTC. And with a battery like that, it can keep the clock for 10 years. Sorry. It can keep the clock for 10 years. But if you take the battery out, it will reset the clock. And with a thing that is sent to International Space Station, that is almost guaranteed that will take the battery out, double check the whole thing, because that's maybe the only little chemical element in this circuit here. And I want to make sure that it works. So it's been gone through all the testing. Actually, there's more testing going through a circuit like that than if you send it into space. Because when our 40 plus satellites went up last year, they went up on an unmanned rocket and were launched into space in an unmanned environment. When we send this to International Space Station, there's astronauts up there, and they really, really don't like that you send something up that may be not 100% okay. So this undergo very strict testing before it actually can be launched up to the International Space Station. The environment it operates in is maybe not as tough as if it was in space, but the testing it undergoes is certainly as intrusive as you can possibly imagine. So here's the Faraday cage. So you can see on the left picture, the Faraday cage there in the bottom. There's a similar lid that comes on top. And that whole thing is getting screwed together, and there's like a plug point on it where the astronauts just plug in the power. The rest runs in there. So we have that little slice there in front, a little 3D printed cover. Our kit can be inside, and they provided power to our stuff, and otherwise they just plugged it in. There's a couple of screw points you can see on the picture on the right hand side, and then it went into the kit here, and the rest of the box are full of these small biological labs that runs inside. You can see there's a fan there to the left of our kit on the left hand side. So there's probably some temperature issues that one could look at here also. So Faraday cage, those ripples down there make sure that no radio noise gets into the box, but more importantly, no radio noise comes out of the box and interfere with the ISS operation. So just remember, whatever happens on ISS, you can't just like jump out the window or the door. You're there for whatever happens up there. So very strict rule set to look at how things are operating up there. And then on this picture here, this is like the live feed from the installation that was sent to our guys in California. to Quest, and they then took a picture and sent us the picture so that we could see the box being installed on the ISS. You can see things are floating a little bit around on the picture here, and it gets into its position. So the box comes up. It was launched with Antares rocket. I think it was number 13 that went up there, and they have all the different experiments from everywhere in the world. And in this case, it's a box like this thing here. It have a specific position where it goes in. So the astronaut take it out of the boot of the rocket there, put it into a position, and put a power cable in and power it up. And that happened on the 19th February at 15:40 and 50 seconds GMT. So everything up there is GMT. So the box is in there, and what they're gonna do is that they're gonna, when the experiment is over, they're gonna take the box out, take the power cable off, put it into the return rocket, which is a SpaceX, since Antares can't take anything back to Earth. It's only on the American side, it's only the SpaceX that can do that. So it goes into a SpaceX and it comes back on Earth, and the whole box went back to Quest. That then will, take it apart again, and they got the SD card out of our kit. And if it wasn't for the lockdown, they will have sent us the kit. But for now, we are very, very happy we just got the data. So this is the data. So I just created this little metadata of what was on the SD card. So on the SD card, there was 15 comma-separated value files. So the CSV files here, you can see here, this is how they were dated. So you can see the 2000, so 6 seconds into it, that was like the SD card came in, and it was powered on, and the battery came on board, and that was actually where the first record then was recorded. And that was, of course, not just after New Year. This is when the kit got powered up. We have since calculated what the right time should be, but for now, this is actually just straight out of the SD card. And this is the last recording. So I had a little program that goes in and read the recording of the first line, the first record in a data set, and the last one. And this is how many records that was captured. So you can see that these two lines here is the one that have all the juice. There's the 500,000 in one and over 1 million records in the other one. In total, this comes to like 350 megabyte of data. So number one issue for us was collect a lot of data. Tick, big check mark, we did that. The other thing that was important for us was that we didn't have a lot of different comma-separated file and things like that, or it didn't stop. And you can see there's two files here. There's like over 2 minutes break, 2 minutes and 47 seconds between the last record in the first set and the first record in the second set. So we believe that some kind of a power interruption. It might be purposefully, it might be not purpose, we're not sure. It might be they took it out because they want to take some data off for some of the other projects and send them down over the radio. But we have two major data sets here. And what we did was that we adjusted the start the date of the first record, and then we saw what was then the correct date and time on the last record, and then matched when we got a message where they say it's now been switched off and it's on the way back. So the last one was, I think, the 19th of March. So you can see it's like off by 14 days in the and it says 2000, not 2020. So there's 1900, a lot of years more that have to be added to that also. But all that is going to be into data. I'm going to talk more about that. So the first thing I wanted to do was to kind of like look at the data, but you double click on any of these files and any of your usual numbers or Excel or whatever you have will fall over, because Excel can take 65,000 records. The smaller of the two data set have 500,000. So over 10 times more data. So couldn't really kind of like use that. So I decided to use this open source language that's called R. So this is a statistical computing language. And the thing is that it's meant to kind of like handle big data and have all the different statistical tools that you want to do and use. And when you have like 1.5 million records of data, you need statistical tools to analyze. You can't go in there and look at the individual data points. So what I wanted to do first was just to see, is there any of the data that doesn't move? Is it some like they're all zero, or they're like, we didn't record that for some reason? Is it like crazy data or whatever it is? So I use this for kind of like analyzing this thing here. And just to give you an example, here's the 2 lines I have to do to just get the first analysis. The first line is how to read a comma separate file. You can see here I called it the data because I actually took the 2 files and I just, smacked them together to one comma separate file. You can do that in, there's a number of tools where you can just put them together. I could probably done it in R also, but decided to do it in a tool I knew. And then there's a header and it's comma separated. And then the data set, it's called D. Just was too lazy to give it a longer, better name. And then you just say summary D. And out of that, you get this thing here. So you're probably going to have a little problem on reading all this thing here. And I'm going to zoom in just now. But just so you have an idea, each of these boxes here represent one of the values that we have. I think there's 43 different values that we collected. So there's like a number of different statistical representation of each of them. So I'm going to zoom in and just show you a few of them. So the first one I'm going to show you here is SCO2 temperature. So our real-time clock also measures temperature. It's a thing that in embedded electronics, a lot of CPUs and a lot of devices that have to keep a certain speed, they also measure the temperature because the device might change how fast it runs depending on the temperature. So therefore it will typically also measure the temperature to make sure it keeps the clock correctly. If it does it, then there's also a good chance you can read that temperature. So I did that. So and we collect the temperature for a lot of different devices because of course our climate sensors, the SW2 and the SW12 will also give you temperature. So we got it plenty. So I'm just taking this first, and you can see there's a minimum temperature of 0.5 degrees Celsius and a maximum temperature of over 1,000 degrees Celsius. So that is probably typical when it starts up and the power goes on first. It kind of like, wobbles a little bit around before it settles for some proper temperature. We knew that, and we decided not to kind of like put into the code, but just record them because we can always clean up the data and come to back. So we rather have the code a little bit more, clean in a sense that just record what it sees, instead of we having, test routines to go in and say, oh, if the temperature is over 180 degrees, it's probably wrong and therefore don't record it. Because that could introduce errors in our code otherwise. So we just recorded everything. But from a statistical point of view here, we can see that, first quartile, I think it's called, is 34 degrees, the third is 36 degrees, and the median and mean is around 35 degrees. So, wow, is it that hot on ISS? Well, it's that hot inside the Faraday cage. So remember, there was a fan there inside the Faraday cage, and it was on different experiments. So I have looked at the other temperature data, and the other temperature sensor will say the same. They'll all say somewhere over 30 degrees. So there's a little bit of heat in there. The next thing is like our SD33. So this is the total volatile organic compounds. And again, there's like some outliers. But you can see here that the median and mean is not the same. So the median is like the middle record of all the records. So they line them all up, all 1.5 million, and they figure out which one is in the middle. And the mean is that averaging all 1.5 million records. So there's a variance there. So there's going to be some stuff interesting to look at here. The same with the CO2 that is then calculated out of that by the unit here. you can see 400 is like the first quantile, and that's actually more or less the way it should be, because that's actually the lower level it can calculate this sensor here. And then it goes from 400 up to 1060, but you can again see the mean and median is like so this is gonna be interesting to look at. And I actually taking that specific thing here and I made a box diagram. I'm gonna show you that just now. I'm just gonna take a couple of others. We calculated the g-force, so we took the accelerometer and we took the 3 different vectors and we put them into one vector, and then we took the minimum value and the maximum value, and you can see there's like 1.6 g in the minimum value and 2.2 g in the maximum value. So this is going to be interesting to figure out, did we screw up in our calculation there? Is it really like that? Because we also have the raw data. You can see in a lower right corner SI20 GX. That's some of the data from the SI20, and we have other SI01 data below. Is a magnometer. SI01.m is a magnometer. So we have like a number of these different values. So what we're doing is that we kind of like have some of the values we kind of like calculate in average, because we have something that's called a FIFO buffer, so we could kind of like read the data out there, because they could vary a lot. A temperature sensor is something where you can just ask once a minute or once a second, whatever. But with the accelerometer, that will vary all the time. So if you have a bump, you have to be able to pick up just at that bump. So we're going to look into these data here. So here's the CO2 box plot. So a box plot is that it will kind of like go from first quartile to third quartile, and the middle second, that's halfway. That's the line in the middle of the box. So the width of the box is kind of like giving you an idea about where all the data lies. And and the small circles after that is the outliers. So all the data, the part that's interesting of the data, is inside the orange box. All the data that's outside the orange box is outliers. So from a statistical point of view, you want to look at the data inside the orange box, because the rest is kind of like that's like stuff that will mess up your calculation. So you can see there that it's like somewhere going from maybe, should we say, 400 to 1,000, which was also the information we got in the numerical value. So we can use, of course, this R to analyze all this thing here. But what we want to do is we want to use R here to clean up the data. So our final work is that we're going to take the timestamp and adjust it with this value that we have to add to it in order to get to the right timestamp. So we're adding this to all the data, this specific value to all the data. So all the timestamps in the records, all 1.5 million, so we get the right timestamp. Then we're going to calculate the position of the ISS. So we're going to have the kind of like the latitude and longitude on Earth, where it'll be right over, using the 2-line elements. I'm going to come back to that. Then we might clean out some of the noisy data point. If it's make it difficult for other people to use it, because there's data points that's noisy and things like that, we might decide to clean that out. We just got the data a few hours ago, so we haven't really made a decision on that. And then we're going to upload it to our sandbox, data.xinabox.cc, so everybody can make graphs and analyze it and see if there's something interesting to find out of the data. There's a lot of data to work on here, so we want to put it up there so everybody can kind of like deduct all kind of different things. But it could be interesting to also figure out where was the ISS at that point. Maybe the gravity or the magnetism happened at a certain time. Maybe there's a certain sleep pattern. Maybe that, whether the ISS in the sun or in the shade, all that could maybe have influences. We have no clue, but I thought maybe we should just actually put the location in so people could analyze if there was any things like that. Let me just talk about what is this thing here with the TLE. So this is the 2-line element set. So this is a kind of like, when you have to figure out where you are on Earth, you have latitude and longitude and altitude. That's your kind of like 3D position. Typical, we just give latitude and longitude because you're stuck to Earth, or whether it's a mountain or, and you're out in the sea, you're on some kind of surface. But when it comes to space, it's a little bit more complicated. Now, especially because the stuff flies all the time, but it flies in a specific pattern. So in order to stay in orbit, then you have to fly at certain speed. If you fly faster, you will leave orbit. You will leave that orbit. You might go to another orbit, you will leave orbit. And if you fly slower, you will crash into Earth. So there's a very certain speed at the level where the International Space Station is. At 400 kilometer, I think it's like 27,000 kilometer per hour you have to fly in order to kind of like keep your orbit. Can't remember the exact number, but something like that. So with a two-line element, I think it's like, they also call it a Kepler element. I think there's 7 different values. Let's see here. So this is like how the two lines are. So in the top box, you can see it says ISS, and then Saria, which is like its satellite name. And there is like, what do we see? 1, 2, 3, 4, 5, 6, 7 elements in the first one, and 1, 2, 3, 4, 5, 6, 7 in the second one. Yeah. So this is the 14 elements that goes into the formula for calculating. So when you have this 2LE, this two-line element, you give it the time into your calculation, and it will say where is then the satellite. So you have all these different elements you have to give to kind of like calculate the satellite position, and you can use that to, for example, when you set up a satellite and it flies over you, when is that actually coming over you? There's a lot of websites that will tell you exactly when it is, so you don't have to do the calculation. But we have to do calculation because we have to look historically how that satellite, the ISS, how that flew. So that was it for me. We're super excited about this kit here. And when we have more information and we kind of like have loaded into our data set and things like that, we will make it very public so you can see the data in your own way. And of course, if you're interested in the data set raw for your own research, like if you want to run your own R and things like that, feel free to contact Judy and she will, figure out a way to get the data to you. Thank you very much and see you next week.